So we have talked about Feynman diagrams. In fact, that was the very last video on this channel. Now let's talk about the Feynman ABCs or the Feynman rules. And of course, the video on Feynman diagrams should be a prerequisite for this lecture. So, well, what are Feynman rules, or why do we need the Feynman rules, right? Well, first of all, Feynman rules are used to compute the scattering matrix, right? We talked about the scattering matrix in the previous video on Feynman diagram, right? And we even wrote some rules, Feynman rules for scalar field theories. In this one, the goal for this video is to draw the Feynman diagrams and evaluate the integrals, right? Or to write down the scattering matrix M, right? So why not start with a very simple toy model, and for which, well, the Lagrangian, let me write that down first of all. So for this, the Lagrangian is 1 by 2. While I'm writing, I would also like to mention that this is for scalar field theory, and so you would have scalar degrees of freedom, which just implies that the order of these terms is not important, right? And it also guarantees that the scattering matrix M would be a scalar matrix, right? Because we are talking about scalar fields for with this Lagrangian, right? So, well, 1 by 2 partial mu phi b partial mu phi b minus 1 by 2. Well, it's a pretty long Lagrangian for a reason, and that is because, well, I have three particles in this Lagrangian, right? It's describing a system of three particles, right? So there are those usual, your kinetic terms and the potential or the interaction term, and we would have those for three particles, right? So, well, let me just quickly complete this. You would have G, phi A, phi B, and phi C, right? This one is A, phi A. Right, now, well, note three things over here that, well, first of all, we have three real spin zero particles, which are particle A, B, and C. And the next point is that these particles are their own antiparticles. So for example, particle A is its own antiparticle. And the third thing is that the mass of particle A has to be greater than the mass of particle B, which has to be greater than the mass of the particle C. So you have some, well, basic interaction vertex would be something like this, right? So this is your particle A, this is your particle B, and this is your particle C. Okay, now the first step is the diagram part, right? To draw the Feynman diagrams. So what's the starting point, right? Well, we begin with the initial and the final states. So for example, you have a particle A, and this is your initial state, you say that it scatters into two particles, particle B and particle C. So these are your B and C lines. And well, we leave this part over here in question, right? Now, how do we connect these lines, right? Well, we have to connect these in all of the possible ways using the interaction vertices. And again, I have talked about this interaction vertices and these external and internal lines in the video on Feynman diagram. So I hope you have watched that one as well. So you know about the things that I am talking about in this video. Right, now note over here that if I take this, let's just pick this diagram, and I rotate the vertices, what happens? Well, we would have, well, you could have something like this, B, A, C. Now this thing is allowed, right? You can rotate the vertices. But what is not allowed is that you say that you, well, maybe you could draw a diagram something like this, right? And this is your particle A, and you label these particles as B. This is not allowed. So what I mean is, well, you cannot change the particle content, right? So these are allowed, this thing is not allowed. Now, at first, it may seem pretty obvious on how do I connect these pieces, right? Or these lines, coming back to this diagram, of course. Now, even though it might seem obvious, you will quickly realize that there are a lot of complicated ways to do so, right? So we will start with an example of a decay of a particle A into B and C, right? So let's talk about this decay, right? So, well, again, we would have this diagram where you would have your particle A, right, decaying into 2 B and C. Again, the question is what is happening over here, right? And this is what would determine the scattering matrix. So, well, what we could do is, well, we could have several possibilities, right? And let's draw them one by one and in the increasing order, right? So, well, first of all, you could have a tree level diagram that would be a first order. So that's simply this thing, right? So you just have this vertex, and there's B and here's C. And so this one would contribute to the, well, it would contribute some amount to the overall scattering matrix. And in fact, it turns out that the tree level diagram contributes the most to this scattering matrix. And well, there is a reason for that, and I'll come to that reason very quickly, right? Okay, so well, you could have another one which is, well, let's draw a vertex correction diagram. So that would be this thing with a line over here. So what is happening is you have a particle A, you have B and C over here, and this line is again your A, and here you have B, and here you have C, right? So these two have switched places when they were here, right? Okay, so let's call this one some M2, right? Now you would have three more diagrams, well, they would be, well, you would have, of course, you would have a lot more diagrams for this specific decay. But, well, we could draw 3 more for the self-energy corrections. And in that, we have particle A and this thing B and C, which is the self-energy part. And then you have it decaying into B, C, where again this line is A, right? So this one is B, this one is C, and again likewise this is A, this line, and this is line B, and this is line C, right? So this would have some contribution to the scattering matrix as well. Then you could have more, where you could have something like this. Let me just draw it. Right, this one where you have A over here, this is your line B, this is C, and this is A, C, and this is B, right? And let's just draw one more, and that would be, and it would be something like this. Again, here you would have A, here I would have C, this is B. Now if this is C, this is A, this is B, and this is C. And you would have more diagrams, of course. You could go to 5th order, and you could keep going on, right? Okay, now what we shall do is we will evaluate each diagram to get MI, right? So MI, which when I sum it over all i's, I would get the overall scattering matrix, right? So how do I do that? Well, I will just use the Feynman rules. Now note that the Feynman rules will somewhat change for the complete or the full standard model, right? Right now we are just looking at the scalar field theory, right? Okay, so, well, if I just quickly go over the Feynman rules that we discussed in the video on Feynman diagrams, well, what is the first step is you label each momenta, or I don't know, I think I should write this down, but of course then it will take me some time to write them, so you have to forgive me for that. Well, number 1 is that you label each momenta Pi, which is the external part. So external lines are labeled as Pi, and Qi are labeled for internal lines, right? And you draw arrows next to the lines, and this just lets us keep track of the momentum flow, right? So for Pi, for the external lines, the arrows should always move forward in time. And for Qi, well, for Qi, it does not matter, right? Your arrows can flow either backwards or forwards. But for Pi, the arrows should always flow forward in time, right? Okay, now number 2 is that for each vertex that appears in the diagram, you write down a factor of negative iota g. So for each vertex, right? So say you have this diagram, and you have this decay of A into B plus C. This thing over here is your vertex, right? And so if for this diagram we just see that there is one of this vertex, so we would just have one factor of negative iota g, right? And g is the coupling strength. Now that I mentioned this thing, that g is the coupling strength, let me quickly go back up here on these diagrams And if you just remember, I just mentioned that the tree level diagram, which is this one, contributes the most, right? And there is a reason for that, and that is this coupling strength G is associated to this vertex, right? Now, if this G is associated to this vertex, well, G is a very small number, right? It is extremely small. And what happens is that if I look at this diagram, right, this one, what do I see? I would have a vertex over here, a vertex over here, and one over here as well. Now, you see you have three vertices, so the factor that would be associated to this is negative iota g cube. Now, because g is very small, let's just ignore this iota and negative iota. Let's just consider this g. G is very small, and if I cube this, as higher as I go in the powers, the overall number would become smaller. And so the contribution to the matrix element, scattering matrix element, would be very less. And if that is very less, the overall probability of that specific scattering process taking place would be less. And that is the reason why tree level diagrams are, well, I should not get rid of that. Okay. That is the reason that the tree level diagram has the most amount of contribution, right? So a diagram with the least amount of vertices contributes the most to your process, right? Okay, so with that out of the way, and that was a very important thing, by the way, but with that out of the way, we can continue where we talked about this negative iota g is associated to each vertex, right? Moving on to rule number 3, for each internal line, so if you have an internal line in the diagram, you associate a factor of iota over q j minus m squared c squared. Well, we would just set c is equal to 1, and so we can just ignore this thing, right? Using natural units, of course. And so this would be minus mj squared. Right. Now, note over here that qj squared is not equal to mj squared, right? And that is because we're talking about virtual particle, right? So they cannot be equal to each other. Otherwise, you also, well, let's not get into that, right? Let's just stop it over here. Moving on to point number 4, the rule number 4 is that for each vertex, you have to conserve the 4 momentum, right? So you have to conserve the 4 momentum. And how do you do that? Well, it's very simple. You just add this factor of 2 pi raised to power 4 times delta 4, the total momentum that is incoming, so let me write it like this, minus the total momentum that is outgoing from a vertex, right? And again, this 4 is over here because we are talking in terms of space and time, and we are talking in terms of relativity. So everything is in space time, right? Okay. Let's move on to rule number 5 is that you integrate. So let me write it down. You integrate everything that you had written from this 1, 2, 3, and 4, right? You integrate it over all internal 4 momenta, right? And how do you do that is you just use this integral 1 over 2 pi raised to power 4 d4 qj, right? where this j is just how many internal lines that you have, right? Because remember, q is associated to the internal lines, right? Okay. And the last step is, well, you just when you do that integration, you will be left with a factor of 2 pi raised to power 4 delta for total incoming momentum minus total outgoing momentum, right? You would be left with this. You just, what you do is, at the end, you just get rid of this and you replace it with iota, right? So you replace it with iota, or you multiply your whole thing that you get up until here with iota, and you get your scattering matrix M. Right. Now, what we shall do is we shall do some examples, and I would like to start with a very trivial example, right? So we would consider a tree level diagram for this scattering for A to B plus C, or this decay of A into B and C, right? So let's start with drawing one possible diagram would be the tree level diagram, and it's just A coming in and, well, B and C going out, something like this. Now, according to these rules that I just wrote up over here, 1 2 3 4 5, let's look at number 1. So you have to label the external lines with pi, and you have to label the internal lines with qi. Okay, so, well, let's see. You have this is your vertex, right? And A, B, and C are your external lines, and you have no internal lines. So you would just label this as P1, this one as P2, and this one as P3, right? Okay, so that is done. The next step is to associate a factor of negative iota g with each vertex. We can see that we just have one vertex over here, so this just comes one time, right? What is the rule number 3? 3 is that for internal lines you associate this factor. But we know that in this diagram there is no internal line, so we can skip the rule number 3. Okay, fine. Let's go to rule number 4. It says that you have to conserve the 4 momentum, and that is very important. So we would do that for this diagram. And to do that, well, what you do is you write 2 pi power 4 delta 4. Now you have to see the momentum that is ingoing minus outgoing, right? So we have P1 is going in and P2 and P3 are going out, right? You can clearly see from these two lines. So minus P2 minus P3. Perfect. Now, what is rule number 5 is that you integrate over all the internal momentum, or the internal 4 momentum, but we know that for this specific diagram there is no internal 4 momentum, so we can just completely ignore the integration. Now if I do that, we can simply move on to step number, or the rule number 6 is to get rid of this factor and replace it with iota. And so then you would have this iota times negative iota g, and that would be iota times iota is minus 1, and that minus 1 would get rid of this minus, so you get plus g. So the scattering matrix, or the scattering amplitude for this tree level diagram is just g. And that's it. You're done for this specific diagram, right? You have computed the matrix, the scattering matrix, or the scattering amplitude, right? Okay. Now let's compute this m for more examples, right? Because that is the task of this video after all. So let's go ahead and do it for some other diagrams, right? Well, we saw from here, I had this diagram. Let me just, in fact, I'll copy paste it. Yeah, that seems pretty neat. Okay, so I'll copy paste this diagram. I'll paste it over here. We have this one, right? And let's just get rid of the unnecessary lines. Perfect. Now let's do the same thing for this diagram, right? Now the first step is to label the internal and external lines. So this would be P1. This is an external line. This little line over here is also an external line, and let's call it P2. And this little line over here is also an external line. Let's call it P3. Now let's label the internal lines quickly. Well, this is an internal line, so let's call it Q. And let me just give it a number. Let me label all the other ones as well. Let's call this one also Q. This is an internal line, and this one is also an internal line, so Q. Now I had P1, P2, P3, and because Q is differentiating between particles already, so I just write Q4 over here, Q5 and Q6, right? Because well, Q is already telling you that the Q is for the internal lines and P is for the external lines, so I don't have to go again and write down Q1, Q2 and Q3, right? I can, of course I can do it, but it just depends on your notation, right? Okay, now let's write down the integral. Well, again, we know the from the next rule, or the rule number 2, is that you associate this factor of iota g, in fact negative iota g. Now how many vertices do I have? I have this one, so 1, 2, 3, right? So a vertex is from which you have ingoing lines and you have outgoing lines, right? Okay, now so I have 3 vertices, so I would have 3 power for this. Then if I go back to the rules, what is rule number 3 is that for internal lines I associate this factor, right? So for in doing so, let's see how many internal lines do I have. I have 1, I have 2, and I have 3. So we have 3 internal lines. So this factor should appear 3 times. So I would have iota over. Now, well, first we have this point C, right? And so let's see, minus M, this subscript C is for this vertex C, right? And now let's see, from C we have for this line C, I'm sorry, I said vertex C, I meant this line, right? This line is line C, and so for this line it has associated momentum Q4, so I would have Q4 squared, right? Likewise, I have iota over for this line B, I have minus MB squared. The associated momentum is Q5 squared, right? And finally, for this line A, this one, I have this thing, minus MA squared. I have associated momentum Q6 to this, so Q6 squared. And then we add, well, from the rest of the rules, you just know that you just add 2 pi 4. This is to conserve the 4 momentum. Well, let's see. You would have a P1 minus Q4 minus Q5, right? So this is for this vertex, right? So you have P1 is going in and Q4 is going out, right? And Q5 is going out, right? So, and then let's keep multiplying others for other vertex, right? You have to conserve the momentum for all of the vertices. So let's do for another one. and let's see, you have Q4 for this one. You have Q4 going in, you have Q6 is also going in, and P2 is coming out, right? So P2, right? And then let's finally for this vertex, you would have again 2 pi raised to power 4 delta 4, and well, you have Q5 is going in, and Q6 and P3 are coming out, right? You can see, right, for this vertex, Q6 is coming out this way and P3 is coming out this way. So minus Q6 minus P3. And now you just integrate over all these internal lines. So we have 3 of them, so we have 3 integrals, and you would integrate it over d4 q. So you have to integrate over all the internal lines. So for internal lines we have q's, right? Q is associated for each internal line. So we have q4 dq5 and dq6, and we should not forget this factor of 2 pi power 4 with each of these, right? And here is your integral written in momentum space. Right, perfect. So we drew a diagram, we wrote down its integral as well in momentum space. Now let's simplify this integral to get a value for, or to get the scattering matrix M, right? Let's compute that. So, well, how do you do that? We have to constrain the momentums, and we do that by using this conservation of momentums, right? We can use this and constrain the momentum. So this thing, for example, is just telling you that this sum should be equal to 0 because the momentum is conserved, right? So this thing has to be 0. And likewise for this one and this one as well. So we will use let's see, let's use this integral, let's use this delta 4 p1 minus q4 minus q5, right? And we will use this to do, let me write it down here, right, to do the q4 integral, right? And so I got this, of course I got this from here. Now, well, what this just implies is that q4 is simply equal to p1 minus q5, again using the fact that this thing just means that p1 minus q4 minus q5 is equal to 0, right? Okay, now what I do is I would just replace this q4 with this thing everywhere in this integral. Let me try something, right? So we have this integral in this whole integral. Let me make it a bit more, well, let's make it red, and let's make these normal. So this is right. Now this is the integral that we have to evaluate, which is in red, right? So you just replace this q4, this thing, with this p1 minus q5 in this whole integral, which is red. So wherever we find q4, we would just replace it with p1 minus q5, right? So let's do that, right? So if you see this integral, well, we can write this integral down as, now we would just have two integrals because we would integrate over q4, right? So we are factoring, or we are getting rid of q4, you could say, right? So you would have minus iota g cube iota over, now you had q4 over here, so right, you see you have this q4 over here, so you replace it with p1 minus q5 from this thing. So p1 minus q5 squared minus mc squared. This c is just the subscript, right? Which tells you that this is for the line C. Right, okay, so now you would have, well, q5, nothing happens to this, q5 squared minus mb squared iota over, nothing happens over here as well, q6 squared minus m a squared, right? And then you have your these things, 2 pi 4 delta, you would have p1 minus q5 for this q4, right? If I go back over here, and this q4 is replaced by that, and okay, coming back here, q5 and plus q6 minus p2, right? Again, this is delta 4, and you would have multiplied by 2 pi raised to power 4 delta 4 q5 minus q6 minus p3, and then you add this integration d4 q5 d4 q6 2 pi raised to power whole 4 2 pi raised to power 4. Perfect. Right, so you can see that we have simplified our integral by using this conservation, right, and writing this thing. So we got rid of q4 in this integral. Let me again go ahead and make this, I'm not going to do this again and again, right, but let's just do it for this this example, right? Let's make it red as well. Now our goal is to solve or to simplify this integral. How can I do that? Well, I can see that if I use this delta function, I can do the q6 integral as well, right? How can I do it? Well, if I use this thing that I just underlined, let me just write it over here. I can write down q5, wait, just give me a second. Yeah, let's not use this integral. This would be easier for q6, right? So we'll use this one to do q6. So I can have, well, this just tells me that q5 minus q6 minus p3 is equal to 0, which tells me that q6 should be equal to, well, if I bring this p3 over there, it is negative q6 p3 minus q5. Now let's make it positive. So you would have minus here, you would have plus here. So that's your q6, right? And we would replace this q6 in this red integral, and we will simplify it, right? So let's do it. Okay, right. So now we would have just one integral, because this q6 would disappear now, negative iota g cube iota over p1 minus q5 squared, right, minus mc squared times iota over q5 squared minus mb squared, and iota over q5 minus p3. Now we're replacing this q6, so q5 minus p3 squared minus m a squared, right? And the other factors just come here. This one, for example, you would have this 2 pi 4 raised to power 4 delta 4 p1 minus p2 minus p3, right? We are just replacing the values of this minus q5 plus q6, right? So that would be minus p3 from this expression over here. And finally, we would be left with d4 q5 over 2 pi raised to power 4. Now I can clean this up a bit, right? First of all, note that now I just have one q in this whole integral, right? And that's just q5. So I can go ahead and I can relabel q5 as just as q, right? I can do that. And so on doing so, I can I can clean this integral a bit. Well, I can throw some constants outside. So I would have 2 pi power 4 delta 4 p1 minus p2 minus p3 negative iota g cube. And you see you have 3 iotas over here, right? So we can just throw these out as well. So I would have iota cube, right? And then the integral is over q's. So everything that has q stays inside this integral, and q5 is relabeled as q. So I have p1 minus q, this thing, right? p1 minus q whole squared minus m subscript c whole squared 1 over q5 square, sorry, let's just call it q from this thing, right? So q squared minus m b squared 1 over q5. Again, I'm making the same thing. Using this, I'm just relabeling q5 as q. So q minus p3 whole squared minus ma squared, right? And then the integral is over d4q over 2 pi raised to power 4. And that's pretty much it. Using the final sixth Feynman rule, if I go back up here, I just get rid of this factor, replace it with I, and I have my scattering matrix M. So now if I look at this thing, I would just replace this with iota, right? I would just get rid of this and replace it with iota. And if I do that, I would get my scattering matrix as iota times iota cube times negative iota g whole cube integral 1 over p1 minus q whole squared minus m c squared 1 over q squared minus m b squared 1 over q squared minus p3, sorry, it should not be like this, it should be whole squared, right, minus ma squared, and the integral d for q5 over 2 pi raised to power 4. And that's it. So this thing over here is your scattering matrix amplitude for that corresponds to this diagram over here. Well, now it looks a bit rough, the diagram looks a bit rough, so let me just go up and just show you a neat version of that diagram. So it's corresponding to this diagram, right? The vertex correction diagram, this one, right? Okay, now we, as you can well see, it is pretty hectic to do this or to write this down, or it's time consuming, but trust me, this is not as time consuming as it would have been without the help of the diagrams, right? Okay, now let's do a few more examples And well, as you can see, the video length is already, we are on almost 45 minutes now, but we will do a couple more examples, right? And we are going now, I would just go over these examples very quickly, right? So I hope you got the idea of how to write down these integrals from the diagram, right? So yeah, so let's just do some more. So let's do for this one. Let me draw it first. So we have this self energy, and so now this is A, this line is A, right? This one is B, this is again A, this is part of the semicircle, this is C, and this line is B, and this is completely line C. Now we have to first label with the internal and external momentas. So this one would be your P1, and this one would be your P3. For P2, you would have P2 would be this small line, right, for this B. And now let's look at the internal, right? So well, these are your vertices. And so for the internal lines or the internal momenta, let's call this one as Q4, and the one that is associated to C, let's call it Q5, and the one with this A, let's call it Q6. Perfect. Now we have three vertices again, so you would have negative iota g whole cube, right? And you have how many internal lines are there? There are three internal lines, right? For each you have Q4, Q5, and Q6. So you would have three of these factors that were associated to internal lines. So Q4 whole squared minus MB squared. Again, I got this because with this line B, we have a Q4 associated to this line B, right? Okay, so right, so you have for line C, you have Q5 squared, and for the line A, you have Q6 squared, right? And then you have this conservation of momenta, that is just 2 pi raised to power 4 delta 4. Now let's check for this vertex. This vertex, you have P1 is going in, Q4 and P3 are going out. Then you have for the other vertex, you have 2 pi 4 delta 4. Let's see, you have Q4 is going in this vertex, right? Q4 is going in, and Q6 and Q5 are going out. So it's something like this. And then for the final vertex, you have 2 pi raised to power 4 delta 4. You have Q6. You can see, right? Q6 and Q5 are going in, and this P2 is going out. So that's it. And of course the we have to integrate it over the internal lines. So you would have three integrals because you have three internal lines, and it would be D4Q4, D4Q5, D4Q6, right? And to each you have 2 pi raised to power 4, 2 pi raised to power 4, 2 pi raised to power 4. Right. So we have the integral in momentum space for this specific diagram. Again, next step is to simplify this, right? To just convert it into one single integral. And we can do that again by using the conservation of momentum. So if I use, well, we can do the Q6 integral by using delta Q5 plus Q6 minus P2, right? Which is this one, right? And with this, we are going to solve this, the integral over Q6. Perfect. Okay, so let's do it. this just tells you that Q6 should be equal to P2 minus Q5. And so again, we would just replace Q6 in this whole integral with P2 minus Q5. Okay, perfect. So we are replacing Q6, so we are just getting rid of one of the integrals. So something like this, iota over Q4 squared minus MB squared, iota over Q5 squared minus MC squared. And now let's replace Q6 with P2 minus Q5 whole squared minus MA squared, right? And well, okay, I'll write down these factors of this 2 pi again and again, even in this example, but for the next one I just write dot dot dot, right? So because I hope that by the second example you would get the idea, right? It's not that tough at all, right? And I hope you can understand it now, right? So you have P1 minus Q4 minus P3 times 2 pi raised to power 4 delta 4. What do I have? Q4 minus Q5 minus Q6 into 2 pi raised to power 4 delta 4 Q4 minus Q5. Yeah, minus P2 plus Q5. So I can just get rid of this Q5 over here like this. And we have two integrals, so those are let me write here, yeah, dq. We got rid of Q4, so sorry, we got rid of Q5, sorry, Q6. Wow, I don't know what's going on with me, but yeah, we got rid of Q6, so we have this thing, right? And here we go. So we have simplified our integral so far by this much. Now we just have to convert it into one integral, and that is, we would just do the Q4 integral, right? A Q4 integral. And to do Q4 integral, we will just simply use delta Q4 minus P2. The simplest one, right? This one, which implies that Q4 is just equal to P2. And now my integral just becomes negative iota g cube iota over P2 squared minus MB squared iota over Q5 squared minus M. Well, we just have one Q now, right? So let's just relabel that Q5 again as Q, right? As we did in the first example, right? Okay, so iota over P2 minus Q whole squared minus M A squared. And I forgot, over here we had MB squared, right? Okay, let's just get rid of this. Now what you would have is, again, you would have 2 pi power 4 delta 4 and P1 minus P2 minus P3, right? Because you replace Q4 with P2, right? And so this is what you have. And of course the integral d4 Q5 over 2 pi raised to power 4. Okay, yeah, like this. Now we have this integral. You know what to do next. You just replace this whole thing with iota, right? Okay, so what goes away is this whole thing is replaced with iota, right? And that's how you get your scattering matrix. So what I would have is that iota, this iota from here, then we have again these three iotas from here, so iota cube, and I would have this minus iota g cube. I can throw that out of the integral. I can throw everything that does not contain q outside the integral. So what else is there is this thing 1 over this thing, right? So that does not contain q, so p2 squared minus mb squared, I can throw that out, and I would be left with 1 over q squared minus mc squared 1 over p2 minus q whole squared minus ma squared, right, d4q over 2 pi raised to power 4, and that's it. So this is the integral or the scattering amplitude that corresponds to this diagram. Beautiful. Now what I will do is I will just draw another diagram, and I would like you to do that integral yourself, right? Or to write down the integral or the scattering amplitude yourself. So the diagram is very simple. Again, it is this thing, right? And this is your A, this would be your B, this line would be C. If this is C, then this would be A, this is B, and this is C again, right? Now the first step is to label external and internal momentas. Then you follow these Feynman rules that I wrote over here. So I will do one thing. I will just zoom this out like this. I hope you can still see these rules, right? And okay, something, let me just make it like this. Now just look at these rules. I'll stop here for a bit, and you can pause the video over here, or let me just zoom out a bit more, or do I need, no, I don't need to. Okay, so you can pause the video over here, you can look at these rules, follow these rules, and then solve this problem that I'm writing down on the later page, right? Solve it yourself. Okay. Okay, assuming that you have paused and looked at the rules, maybe even screenshotted them or whatever, I would now go back down. Coming back here, okay, let's just zoom in a bit. Perfect. Okay, now this is the diagram that you have to evaluate, and what I will do is, of course, I will give you the answer that you should get at the end. Is this amplitude should be iota minus iota g cube I cube 1 over p3 squared minus mc squared integral 1 over p3 minus q squared minus m a squared 1 over q squared minus m b squared d4 q over 2 pi raised to power 4. So this is what you should get when you do this diagram, right? Okay, now well, there are several more diagrams that I would love to do over here, but I guess I'm going to, because the video is already getting very long, I'm going to skip to the well, to the last diagram, right? And we would consider for that, let's consider an example where we have a scattering for a plus b to a plus b, right? And we would consider this at a lowest order. So the lowest order, the diagram that you should or you would have is something like this, right? And here you have a, this is a b, this line is c, this line is b, and this line is a, right? Again, according to this scatter. Perfect. Now let's follow the rules again. So labeling internal and external momentas. So this one would be your P1. This should be P2. This is an internal line. So this should be Q3. And the external lines, this should be your P3. And this, let me check. This should be your P4. Right, and then, well, this should be your Q5, right? Okay, perfect. Now you can see, well, you have this and this, so you have two vertices, so you would have iota g, negative iota g squared. Now you have one internal line, right? That is this line C, right? This one. So you would have this factor associated to it, iota over it's line C, so minus mc squared. For line C, you have associated momentum Q5, so Q5 squared, right? And then what you simply do is you just conserve the momentum with this 2 pi raised to power 4 delta 4. You have P1 plus P2 minus Q5 D4 Q5 over 2 pi raised to power 4. And of course, this we are integrating over the internal momenta Q5, right? So what you do from here is simply just you use this thing and you write Q5 as P1, or I'm sorry, let me see, did I make a mistake? Okay, so what you do is you well, you would have another delta factor, right, for this other vertex, and that would be delta 4. You would have this Q5 going in minus you would have P3 and P4 are going out, so P3 minus P4, right? So you use this one and you write Q5 simply as P3 plus P4. Yeah, I made a mistake over here. Well, not a mistake, I missed this factor of we had to conserve the momentum at each vertex, right? So this one was for this vertex and I missed one for this vertex, right? And so that's this one. Anyway, now I have Q5. This thing, I would just use this to do the Q5 integral. And what happens is I'm left with negative iota g squared iota. We just have this one iota right over here, so we can just throw it out like this over here. And 1 over P3 plus P4, right, replacing Q5 over here, squared minus mc squared, and then this factor of 2 pi power 4 delta 4 P1 plus P2 minus P3 minus P4, right? And now just using the last Feynman rule, or the sixth step, that was to just get rid of this thing, replace it with iota. So that just gives you the scattering matrix, and that's, well, it would be g squared. Let's just multiply these iotas, so they would cancel with this negative sign, right? So these all just go away, left with g squared over p3 plus p4 whole squared minus mc whole squared. And this is your scattering matrix or scattering amplitude for this a plus b to a plus b scattering, right? Okay, wonderful. Now you could do as an exercise, right? You could do one for a scattering that looks like this, me just draw let's something like this, right? And over here, this is your A, this is your B, this is your A, and this is your B. So let me just draw these arrows that this is going in like this is also going in like this, and these are coming out. Now just label the internal and external momentas, do the same thing, same steps that we were following for every example, and it should be a piece of cake to solve this diagram as well. The answer you should get is m is equal to g squared over p2 minus p4 whole squared minus m squared, right? Okay, so yeah, so this is the scattering amplitude that you get corresponding to this diagram. And if I go back here, this and they look the same, right? They're not the same diagrams, that's important to note, but they are the lowest what do you say, they're diagrams at the lowest order, right? So you would get one contribution to the overall scattering matrix from this one, so let's call it 1, and the other one you would get from this. So when you add m1 plus m2, right, these two let me just, yeah, so this one and this one, when you add these two together, you would have a leading order matrix element, and well, that's just your I don't know if I'm calling it matrix element. Well, I should call it the amplitude, right? The scattering amplitude. Perfect. Now let's just stop this video over here. It has gone way over time, but I hope that you understood something from this video. And if you get a hold of what you're doing, it is actually pretty interesting, and it is fun to draw these diagrams and write down the integrals. You could come up with your own ideas of how the scattering happens, right? So what happens in between this area over here, right? So it gets interesting. That's my point. So let's end it with some remarks that, okay, so when you are evaluating various Feynman diagrams, and in fact, especially the ones where you have to add several contributions, right? Well, these were very simple. We just had one line, right? Internal line. Well, consider this one, for example. You had to add this contribution of this energy, right? Self energy. Or even if you think about, if you look at this diagram, this one, so, or well, there are a lot of complicated ways in which you could have these diagrams. So the point is that when you are evaluating these Feynman diagrams and you have to add this contributions there, it is actually very helpful to start with all of the external labels first. So what I mean by that is you just draw these lines or these external lines, right, like this, and you write these A, B, C, and for example you have D over here, and you label these momentas like this: P1, P2, P3, P4. So these are all the external lines. So you label them with the external momentas P, and then you fill the rest of the diagram, right? So you add whatever interaction is happening in this part. So this way you can avoid mistakenly using a momentum P, right, for distinct particles in different diagrams. Because it is important that when you add these m's, right, add these m1, m2, so mi, you're adding these mi's, that a single external momentum label, example this P, it always refers to the same particle, right? So if we're talking about electron, it should refer to the electron. So if you have a P is associated to electron, and for example, we did in the video on Feynman diagrams, if I remember it correctly, and we gave K to the momentum of the positron. So wherever we had K's, K1, K2, that was associated to positron, and wherever we had P1, P2, and so on, that was associated to the electron, right? So that's very important, right? Okay, now again, I hope that this video was very helpful to you to understand on how to draw and then write down the integrals of the Feynman diagrams, and how to even solve those integrals and write down the scattering amplitude for the Feynman diagrams. Next time, we will talk on QED, quantum electrodynamics, and what we shall see is, well, we will see a lot of things, of course, but we will look at the QED Lagrangian, and from it, the corresponding vertex factor, propagator, and other stuff, right? And we would use that to write down the Feynman rules for quantum electrodynamics, and we would also compute the scattering amplitude for one diagram, right? So yeah, that's it for this lecture. Hope you understood. Hope you can now solve these diagrams, and I would expect you to really do the problems that I just mentioned in this video to write down the integrals yourself. And I also gave the answers to that at the end, so you can check with that, right? Okay.